you see the stream
On
the way
Twitch?
the way it's looking? There's like a little bit cut off on the.
Oh, yeah, I see. Is
I
there
don't
a
know
way
if
to
that's.
specify?
I don't know if that's the like aspect ratio of your monitor. Then it might be harder to. You're right. You might be able to like center it or something. There you go. Testing, testing. Okay, test successful. Should I click this run 60-second ad break button? Seems kind of terrifying. I can't do it. Sorry. All right, it's 6:30.
Alright, so welcome to Crypto 2. So first I'm gonna clone the repo and show how you can access it in the Docker and then through the other tool that we'll be using today. So switching over to here. Sorry about that. Is there some way I'm able to full screen this?
I feel like you're just gonna make the browser bigger. F11, just go full screen. I don't know what'll happen to the stream, but I'll let you know.
Did that change anything?
Yes.
It's
Okay.
okay.
It's fine now.
Okay, so then from here, I'll just write the link down and you guys can copy as we go along. So you'll get clone, HTTPS. Alright, so then we'll just move this back one directory. Yeah, we'll move it back one so it's visible from the other one. And then to access the other tool we'll be using, it's just the same link, just switch it to 4/8, and then you should be able to see it here. Is that, everyone have that?
Yep.
Okay. So then for today, so once you have that, then we'll just start going through the presentation for today. So in last week, we covered stuff like XOR and simple modular arithmetic. For this week, we're going to cover, or for this day, we'll be covering Diffie-Hellman and RSA, continuing on with modular arithmetic. So then, just going over briefly what we went over last week. So within cryptography, we're looking to utilize properties in mathematics that make it non-trivial to crack essentially our crypto systems. So continuing on with that today, we'll be looking at more difficult crypto systems, more so than just XOR and stuff like that. So firstly, I wanted to give a thanks to CryptoHack and their Docker and website that they essentially open source for the community to use and practice on their website. I personally have sunk a lot of time into their website over the summer and ended up nearing top 100 on their website until school started, so then I really don't have much time to sit there and sink hours into it anymore. But it's a really great resource if you're interested in cryptography. And a lot of people within the Discord are very helpful if you have questions regarding solution methods to different types of attacks on different crypto systems. So moving on, we'll be starting off looking at the Diffie-Hellman public key protocol. It was one of the earlier versions of what we would call a public key crypto system, except it's not solely its purpose is not to encrypt, but to define how this sort of protocol would work. So if you remember from last week, we looked at the one-time pad, and in that you use the same key to encrypt and decrypt. This Diffie-Hellman public key protocol is different in that you're going to have a key for decryption and encryption. So that's a bit of an advantage over stuff like one-time pads, because once you encrypt your message, for an outside party to decrypt that message, you have to come up with a way to securely transfer the key to decrypt. And in order to do that, I've heard of things as such as like actually physically handing it off, because that's one of the more secure ways, because you know that there's no interference midway in transit. So that's what the public key cryptography tries to alleviate, that burden of having to hand deliver a key in order to decrypt a message. So as I said, asymmetric and symmetric cryptography are two classes or definitions of how a crypto system would work. So in asymmetric, we have different keys for encryption and decryption, also called public and private keys. Examples of this are the Diffie-Hellman key exchange, RSA. There's also El-Gamal, elliptic curves, and then likewise for symmetric, we'll be using the same key for encryption and decryption. So that'll include one-time pads and AES. So now looking at how we would construct this protocol, we have a prime modulus P. We select P to be prime, because otherwise, if you're able to factor the modulus, then you can, it would make computation of our secrets much easier. So that's why we select the prime. We have our base G, which could be what they would call the primitive root of P, but it doesn't have to be. It would dictate what sort of group you would create. So now the typical way they explain cryptography is with two parties, Alice and Bob, so we'll do the same. Alice and Bob will call their private keys small a and small b, respectively. So then we have their public keys, which are uppercase and A and B. So to obtain the public keys, what we do is we take the base G, we raise it to the power A, and we take mod P, and then we'll have the public key for Alice. We do the same for Bob, and we'll have his public key. So then that's the benefit of this sort of crypto system. Rather than XOR, where we have to ensure that delivery is secure, with the public keys A and B uppercase, we're able to communicate them over an insecure channel, because if you solely recover those, which are equivalent to G to power A mod P and G to B power mod, or G to power B mod P, you can't easily calculate back the private keys from that. So then after both parties exchange those, then they'll just take the result and raise it to their own private key, giving them the shared secret. And that's what we're trying to protect, as the shared secret, and that's why public key cryptography is convenient, because we're able to communicate those public keys without the risk of them being intercepted, and then being able to decrypt what our message would be, or in this case, calculating our shared secret, because it wouldn't be the same as if you had the private keys. So then the reason that this whole crypto protocol is effective is because of the discrete logarithm problem. So normally with logarithms, you're able to use different properties and rules to rearrange the terms in order to get what a power would be, but that's not quite the case when we are taking mod. It turns out to be a much rather difficult problem to solve. So that's why it's convenient to use Diffie-Hellman. So now we'll transition over to just a small demo of Diffie-Hellman, and then So yeah, if you want to go into the CryptoHack Docker with localhost on port 8888, and then to the Diffie-Hellman directory. So for this, we have just our output. So one thing to notice right away is this is just for a simple explanation, but we're using extremely small values. So we're easily able to enumerate possibilities because they're that small. Other cases it wouldn't be this simple, but for this demonstration it is. And then I also explained how I generated this, but
check the screen. It's one of the
oh,
functions.
weird. Okay, my bad. So in this case, we're using pretty small values just for the sake of simplicity. So it makes it very easy to recalculate what these could be. And then I use them in a specific way to generate a ciphertext. So reobtaining the values, you can reobtain the ciphertext. So then looking at the redacted source, which is something that you would see in a CTF where they would give you the source used to generate the parameters, but in this case they would remove the part of the flag that would be critical to solving the challenge. In this case, I redacted it. So, and as well as the private keys. So the way I was using it this way was I would do the computation from the previous slide, and then once I determined the shared secret, I would take the SHA-256, which creates a 32 byte hash, and then I also chose the flag to be 32 bytes. And then I would just XOR them together. So without being able to find the SHA-256 of the shared secret, it becomes difficult to solve. So just to note, just to show that the shared secrets of B raised to A and A raised to B with the public to private, just to show that those would be equivalent, I put this assertion. So then how we would approach solving this would be, so what I did was I took the ciphertext from that output. So I create a byte array from hex, so this should be 32 bytes. So then we know these values, which just knowing these alone is not enough to reverse back to getting or recalculate to getting the shared secret. So since they were so small, an easy way to calculate this is by enumerating through all possibilities. We only have p minus 1 values that it could be, because when we take mod p, anything 13 or greater will be we'll subtract a integer multiple of p from it. So the resultant shared secret can only be from 0 to 12. And just to note, I put some resources here of different algorithms in the case that you believe that you would be able to calculate. For things like Diffie-Hellman, it relies on the fact that we have a squared prime, or a power of a prime, and then we can essentially recompute this in a different way. And those are just different ways you can attack Diffie-Hellman style crypto systems. So what I did here was putting in the base result and modulus. So in this case, G would be the base, result is going to be our public keys, and then modulus P. We enumerate through all the possibilities here for this in this for loop, and from there we recalculate the same way that they would have calculated shared secrets, and then when we find that, we can return that, and then we are able to obtain A and B. And then using A and B, we can calculate the shared secret here. Oh, my bad. So the way I used it here was that not using the shared secret, but rather I used the two public or private keys to create a SHA-256 hash and then XORed that. So doing the same here, once I obtain those from enumerating all possibilities, we're able to recalculate the hash and then XOR it with the ciphertext. Doing that, oh, so apparently I cannot run this from in here. So I'll have to use the other one as well then. So upon running that, we can redetermine the flag. So yeah, that's just a simple explanation of Diffie-Hellman. It definitely gets much deeper than that, but I don't want to get too into the details that people get lost with that. So then transitioning back. So the RSA crypto system, which was created by three cryptographers, Vest, Shamir, and Adelman. It's similar to Diffie-Hellman, but not quite the same. One crypto system that is really similar to Diffie-Hellman would be the b01lers. Oh, sorry about that.
Yep.
Wait, what? Alright. So RSA, the acronym stands for the three creators of it, Rivest, Shamir, and Adelman. So it's also a public key cryptography system. A little different from what we just saw, but you'll see some striking similarities. But the main difficult problem within this is that when we take a grouping of primes and we multiply them together, it's difficult to undo that if you are unaware of what those primes were, which is called factoring or prime factorization. So before we get into all the minor details of RSA, generically, we have two large primes, P and Q. Multiplying them together gives us our modulus F. And then we'll have values E, M, and C. So when we take the value M, which would be our message, raise it to this E, which would be a public key, that'll give us our ciphertext mod N. And so now when we look at more of the specifics of it, it's the same case for the modulus, P times Q, in a textbook. So this is dealing with a textbook case. In practice, you wouldn't use solely this. You would probably have some sort of padding employed here, among other things. But it's better to start with the textbook case and build your way up. So what we have here, as I said before, our public key is going to be called E. We select that our E is going to be co-prime to our so this symbol here, the circle with the O with the line through it, is called Euler's totient. So what that does is it counts the number of relatively prime numbers to this number when you iterate from I think 1 to this number. So what that essentially means is that we're looking for E and phi of n to be co-prime. And in doing so, that means that our private key D will exist, otherwise it would not exist. And when we have that, we're able to calculate D as D times E congruent to 1 mod the Toshian of n. So what that means here is that E and D have a special relation, meaning that our D here is what we would call the multiplicative modular inverse of E. So when we have that, when we multiply them together, it'll give us 1 under this congruence. So that's just a specific property of RSA that's very important to why it works. So moving on to the encryption. So it's pretty similar. It's exactly the same actually to what I showed on the previous slide. So we'll have our modulus n, our message m, which we'll treat as an integer, and we'll raise that to the power e under mod n. That gives us c as before. So now decryption is a little different. So what we have is our value of c, which remember c is equivalent to m to the e mod n. When we raise c to d, that's e times d, which remember are multiplicative modular inverses. But the reason why we're able to decrypt using d is because of this theorem called Euler's theorem, which is a generalization of Fermat's little theorem. So for an integer a, when we raise it to phi of n, it's congruent to 1 mod n. And remember, the two are inverses of each other. So another way of writing out this portion is that e times d is going to be a scalar multiple of phi of n times k, which will be the scalar, plus 1. And all that's really saying is e times d divides by phi of n, k times, plus 1. So when we raise m to phi of n, which will be e times d, that'll be congruent to 1 mod n. So then, when we raise m to phi of n, that's congruent to 1 based on Euler's theorem, mod n. So then when we raise it to the multiplication of e times d, that gives us phi n plus 1, remember from here. So then that's equivalent, so from this line here, that'll give us 1 for this term under this modulus, times m will give us back our original message. So then that's how decryption would work. So now we'll consider a small example in how to construct RSA. So this is how this would be how a small example of how you could generate RSA in Python. I'm only using Python in this example and the PyCryptodome library, as well as just GCD from the math library. So what we would start by doing is we'll generate 2 primes p and q. I chose. Wait, really? Just set it. It keeps like resetting, which is weird.
It's funny.
Okay. Sorry about that.
No worries.
So this is a small example in generating an RSA example. So only using the PyCryptodome library here, math library. So we have 2 integers p and q. I'll use the PyCryptodome library function, get prime, to generate a prime of 512 bits. I chose e here to be this value, which is also equivalent to this, which I believe, if I remember correctly, is 2 to the 15 plus 1. It's prime number used quite frequently in RSA because it compromises, or it's a good balance in between speed and security. So then to calculate our modulus, it's just a multiplication of the z primes. Then I just check here that phi of n. So one thing to note here is that that function phi, or the totient of n, when we calculate it for a prime number, it's going to only be the prime minus 1, which is a property of the function, as well as the function is what we would call multiplicative. So we can take the factors, calculate it separately, and multiply them together. So that's how we're doing it here. We're taking 1 minus this prime p times 1 minus this prime q. So then here I'm checking that they're co-prime. And then from there, this worked out, so then this would evaluate because of an assertion. So then I calculate the modular inverse of E under this value of the totient of n, giving us D. And then here I just created a small message, just asserted that it was less than n. And then I created this bytes to long using the PyCryptodome bytes to long function. And then, as before, we're just encrypting it, taking the message raised to E mod n. So then we'll get back this integer. Looks nothing like a string of text. So then to decrypt that, we'll raise it to D as I explained before. And then just to show that it is equivalent to the message M, I did an assertion here. We get this back. So to convert this back, we'll use the PyCryptodome function long to bytes. Long to bytes gives us the string back that we inputted here. So that's just a small example in how RSA works. So now we'll take a look at 3 different exploits that you can use on an RSA system. So the first being, we will look at first the one called Q. So the prompt for this reads, can you recover my 4-digit bank PIN? So here's the modulus n, the public key E. We're using 3 here, which is the smallest possible value you could use for E. And then we have a really small ciphertext here. I'll give you guys a few minutes to think about what the possible attack here would be. And then additionally, I'll just go to the source given. So here we're using Sage. Sage is a open source mathematical software built out of Python. In addition, we're using PyCryptodome again. It's very convenient in cryptography challenges. So here we're using Sage. As I said before, it's just a math software built out of Python. PyCryptodome again. So this time, remember, it says 4-digit bank PIN. So this here would contain 4 numbers. So we have value of 3. We're just generating primes. Just keep trying until we get something that will be able to generate a modular inverse. So just ensuring that we get something that will work. So then we calculate n here after we get these 2 primes p and q. And then from there, we'll just convert this 4-digit bank PIN to an integer, raise it to E, and then that's our ciphertext. So I'll give you guys a few minutes to think about it, see what solutions you come up with.
What about this seems vulnerable? Any ideas? Guesses? Thoughts? Something about that encryption was wrong.
So I'll start going through it now. So one thing to notice is that if we're using a 4-digit bank pin, the largest value that we could have for a string as that would be 4 nines in a row. Because if we use, so like in terms of ASCII, our values for 000 would be less than this. So we can check that that is less than our modulus n. So if we, from here, we'll import this function, bytes to long, converts bytes to a long integer. So if we check that we think that 4 nines would be less than the modulus, we can simply do this. To check that, runs cleanly, no errors, so we know that that's true. So what that means is that when we take our message of m, even if it's 9999949s, raising that to the third power is still going to be less than n, so we never take modulus of that number. So we can simply calculate the cube root of this ciphertext here, and we'll reobtain the value of m, because right now this represents m cubed. So the way we can do that is I like to use Sage to do that. So I'll import Sage using this line. I'll take my value of c, or we'll call it m. We'll say m equals, and then just so that Sage knows that we want to deal with the integer class within Sage, we'll say integer c dot nth root 3. So what this means is we're going to take the cube root of c here, and then just so we can convert it back, we want to take this.
Do you think you can increase the font size a little bit? Or just
oh, yeah. Is that better?
Yeah, that's better.
Okay, I can't really like zoom in or stuff because of, I guess the issue is like using i3. I guess is the problem.
Yeah,
that it keeps switching. But so we'll take this function from PyCryptoDom and we'll import it bytes to long. So assuming that this properly calculated our value, if we convert it back, so we'll do print m. Oh my god. My bad. This is supposed to be long too, but it's the other way around. Right. So then you get back that the bank password or bank pin was 4321. So the key takeaway here is that if you have some sort of knowledge of the plain text, that you can otherwise make some sort of assumption and check, that's what we did here. We checked that in the case of the bank pin being the largest possible value of 4 nines, that we would be able to simply take the cube root because we never take modulus. So all that's represented is here. Here is m to the third, not m to the third mod n. We never take modulus. So with that, that's just an example of like if you know something about the plain text, which is a pretty common theme, in crypto CTF challenges, that you're able to leverage some sort of other hint, but in this case you leverage the message instead. So now we can move on to the next example. So for the next one, we'll be looking at a factoring vulnerability, or just a simple case when we factor, how do we get back that message? So that'll be in day 2 examples, multi-prime. So switching over. So looking at this, it looks pretty standard. Reasonably okay value event. Typically, if your end value is...
Check the display again, I think.
Oh my. This is called... sorry about that. So, usually around 256-bit RSA, I believe, is where factoring becomes more or less infeasible. I believe it's around there. But in this case, I already told you that the vulnerability was that we're going to attempt to factor n in this case. So, additionally, we're going to take a look at the redacted source. Similar as before, we're going to use PyCryptodem and Sage. This time we're going to use a flag format, flag, curly bracket, stuff in between, closing curly bracket. Same value of E as before. So what we're doing here is we're going to generate 4 primes, all 64-bit. We'll calculate phi of that, which will be, as I said before, phi is a multiplicative function, so we can simply consider the case where we're using all 4 primes, take -1 of each, multiply the results, and then we'll calculate n. We're going to, I added this when I was developing it, but that's not super relevant to right now, but then we'll check that it's coprime. And then we'll calculate d, the inverse mod. So in Sage, that's how we calculate modular inverses. We'll say inverse underscore mod, our value that we want to get the inverse of under which modulus, which will be phi in this case. And then we just encrypt it here, m to e mod n. So give you guys a few minutes to attempt that, or if you want to just take a look at this solve. Okay.
Can you go back to the source code?
Yep.
Any ideas? Alright, we could probably take a look at the solution.
Yep. So I can just do this one live. Where did that go? So I already told you guys that the idea here is that we're going to factor, so I'll just explain how we would approach that in we'll use Sage for this example. There's other factoring tools that you can use. FactorDB.com is a very helpful resource because beyond just using general algorithms to factor, people will upload factorizations. So in the case that a tool cannot algorithmically calculate it, someone might have just uploaded it, and that might be helpful, but that is not generally going to be the approach that you're just going to try to factor it every time. There's a lot of other ways that you can break RSA, but for this example, the way we'll do that is we'll say factors equals factor n. And then we'll, oops. So here we're going to import Sage, and then the factor function will attempt to factor. We can print them out. So if we give it a few seconds, I believe it was. What? That is interesting. What? Same thing. Let's see if this finishes.
We can't see anything on the screen. Just
Oh, really?
you're trying to just share the.
Let's see. It's called on okay, there we go. So I think there's an issue with importing it after the fact. I override it or something, but so we call this, we factor this value, obtaining these four. So remember we used four primes in the generation of it. So assuming that these are correct, we can check that. So what we'll do from here is for each prime we want to calculate our value of phi. So for factor in factor, what we're going to do here is iterate through each one of these. This will generate a list when we factor. So what we're going to do here is phi, we're going to multiply it each time with each factor minus 1. So then when we do that, one thing that Sage does is if you have prime powers where you have 2 to a certain power, it will put the base of that number and then the power in the second entry of a tuple. So since we don't have powers here, it's just going to put them one by one. So when we do that, we'll obtain back the value of phi, and then further we can check that this worked. So we have a value of E, here is 65,537. Calculating the private key D, we'll take E, and then we'll take phi, and then we can check that that runs, so that should be good. And then what we can do here is take our value of C and D, and then we'll decrypt from here using C power D mod n. And then from iCryptoDome, we're going to import long 2 bytes. And then we'll print that out. So then you get back the flag primes, exclamation points. So yeah, this is just a general, very basic CTF challenge way you can attack RSA. Usually you can try to factor n, but that's not generally going to work in every case. If they use a sufficiently large prime factor, P and Q are both large enough, it should be infeasible to factor. You might catch a break if it's on factor DB, but in general you should approach it as something you can try, but not the end-all method for breaking RSA. So then for our Next example, it'll be in day 2 examples, Hastad. Oops. Okay. So in here, a little different from before, we're given C1, C2, C3, N1, N2, N3. What this means is we have a ciphertext 1, we have modulus N1, and C1 and N1 correspond, as do C2, N2, and C3, N3. So then if we pull up the redacted source, in this case, okay, so what we're doing here is we're generating primes P and Q. Same thing, N is equal to P times Q. And then we're doing this for 3 iterations, so we'll make 3 values of N. And then we're only using one message here. So that's the key vulnerability that I'll go into more detail about, but there's only one message. So those ciphertexts are representative of some encrypted message, but they're all the same. So then here we're also using public key of 3. So then all we do here is that we check that when we raise n to that it's greater than n. So the only reason I was doing that was to ensure that when we encrypt, that we don't have a repeat of the prior example where you can just take the cube root of n. Because in that case, then the point of the challenge is not there. So then what we do here, so same value of public key here, we just encrypt using 3 for all of them, and then as you saw here when we print them, this is the output here. So I'll give you guys a couple minutes just to think about it, see if you guys come up with anything. Why does it keep switching? What is this? Okay. So this is an example of a well-known attack on RSA. And then by the title on the slide, it's called Hastad's broadcast attack. So when we have a message all under the same message, and then we encrypt it using different modulus each time, when we obtain 3 ciphertexts, notice that 3 corresponds to the public key here. Oh my. So the whole point of the attack is that when we encrypt the same message, when we reach k messages where k is equal to or greater than the public key, then we have a vulnerability. Then we can attack and reobtain what that original message was. So the way that we do that is we'll take the grouping of all 3. So with C1 to N1, C2 to N2, C3 to N3. So that's what I've done here. I've created 2 arrays. So what we can use is called the Chinese remainder theorem, or as in Sage, it'll be the CRT function. And essentially what that's saying is that we have, so for the first ciphertext, we'll have C1 is going to be congruent to that value of m raised to e mod that first value of n, C2 and N2. So it'll look something like that. So what Chinese remainder theorem will allow us to do is we have essentially three properties of m to the e here. So we know that m to the e mod n1 is going to give us c1, m to the e mod n2 is going to give us c2, and so on. So what this theorem states is that we can essentially recalculate using this sort of relation. Like if you've ever taken linear algebra, you have systems of equations and you kind of solve for the values. That's kind of the same thing that we're doing here. We're using the system of relations and we calculate what this m to the e is because it's going to be the same in all cases. The only thing that differs is that C1, C2, and C3. So what we do here is we take the ciphertext and the modulus for each corresponding. The output is going to give us m cubed. We take the nth root of that, and then the nth root should give us back the original message. So testing that. Oh my god. That is pretty interesting that that does not work. What? Of course. So reran it. I'm not sure what happened there, but same idea. We're gonna same message, 3 modulus, 3 corresponding ciphertext. Chinese remainder theorem allows us to reobtain what that m cubed value is. So taking root of that gives us back m. Transforming that from a byte to a long, or bytes to a long, or long 2 bytes, my bad. That gives us back the original message. It says, here's my secret message. So let's see. So what's left in cryptography that we didn't touch on is stuff like AES. AES at the surface is somewhat similar to a one-time pad. They're both using the same key for encryption and decryption, but when you really break down AES, it's extremely different from a one-time pad. There's many more moving parts involved, but there's a lot of different modes that exist within AES. We have ECB and CBC. If you're interested, definitely check those out. But they're come up pretty frequently in CTFs, but not too much. But then we have additionally other stuff like elliptic curves, which are quite difficult to understand, and then stuff like post-quantum that comes up now in CTFs a little bit, it's starting to be more prevalent. So then just examples of those are using lattices, which are kind of similar to a matrix, but there's many more details that go into how that works. And then stuff like multivariate, solving like multiple variable equations as a cryptography system. So yeah.
Thank you very much, Brandon.
Thanks. Sorry about the multiple times that the screen went away. I didn't realize that was an issue that I had with i3.
Working. Thank you.
Yep.
What do we have tonight? Tokyo Western starts. That starts in a half an hour. So if anyone's interested in playing that, I suggest playing it. It's supposed to be a hard one, but should be good. Next week we'll have the cone trainings. I'll be leading those. Should be good. Assuming I can make all the slides nice and perfect. And make sure demos work, as half the time they don't end up working the moment you have to present them. But should be good. Come and see me lead that. But I think that's it. So enjoy your Friday night.